Okay. It's my pleasure to come to Ann Arbor. I've been here once before, but it was basically a short visit. And now I see the full size of university and can talk about topic I like, which is, I think, let's say, delicious in various aspects. So I would like also to introduce my colleagues, which contributed over, let's say, last 10 or 15 years on the topic, and Leonid is here, and Maxim Surov and Sergei Gusev, one of them younger, one is older, and they're associated. Maxim now is postdoc in Trondheim, and Sergei is an associate professor in St. Petersburg University. Okay, so what I'm going to talk today is eventually I have a big schedule which I'm not going to complete because I changed it yesterday after the discussion with a number of colleagues I already met. And Jesse suggested very tough program. So I mentioned only topics which might be of interest after the talk to discuss with you if you get interested, especially on, let's say, sensitivity of gaits to perturbations. This is classical topic you, I think, invest time. Let's say various type of manipulation. I tried to make this experiment after the lecture and hope it will work. And then also on various type of learning capabilities, we need to use, let's say, control techniques. Because I think it's, we have a good opportunities to really overperform various type of machine learning techniques with specific representations of trajectories. And then I also met one of your students who really tried to develop, let's say, not standard robotic device, but suit for rehabilitation. And it's about sit down and rise motions, chair rise motions for robots, which we can learn from the human abilities. So, but this could be after the talk, if we will see. So main task is eventually to talk about very specific example, which I don't know who invented first, but it was really now blossoming number of papers published about compass biped. And we start with that. So compass biped sees this mechanical system like a Euler-Lagrange equation, but we see behind it is really walking machine. And we're interested to understand what this walking machine can do under certain control inputs if we also induce various type of updates. And the topic I'm going to present today is partly about the task listed here. It's not just motion planning, mostly it's about, let's say, control design. Because when we derive this type of uniform strategies in different sense to stabilize various trajectories, we will come to the full-size project on motion planning, and this will be outside of the 45 minutes, but we can discuss it later on. Okay, so what the problem I would like to formulate in details is about this machine. I learned it from Mark Spong, physically, when I was quite young. So system is completely passive. What does it mean? It means that it has zero input on 2 degrees of freedom. It's a double pendulum, which is symmetric. It has 2 masses and legs and mass and torso. It's easy to write equations of motion, but this is a very good example for control people because it has very good control, 0. And it has a number of interesting properties. We could understand why this control is so good. And let's say discrete dynamics basically update whenever this machine hits the ground. The stance lag, its stand during the step becomes changed with this lag. The stance on this becomes a swing lag, propel further and go down. So basically, the equation for switching is given by one scalar algebraic relation on configurations. And the system evolves in 4-dimensional state space. So we have 2 configurations, 2 velocities, and this is cylindrical space where solutions should hit and then update their velocities. And due to the conservation momentum, velocity update will be linear, which is maybe not true, but let's say close to reality. And this update of, let's say, configuration is just relabeling. It's not necessary to be done like that, but it's simplified representation. Okay, so, and what the task, typical task to find a gaits and understand stability and instability of that machine, or periodic gaits, one-step gait. Okay, I would like to make a number of pictures just to visualize what you need to compute, not to how to compute. So we have 4-dimensional space. Can you imagine 4-dimensional space? Let's say it's difficult, so visualization will be in 3D. So we have a switching surface, and then we have a continuous arc of it's the solution of Euler-Lagrange equation. Then we hit this surface, and we have impact, and it returns back. And the typical way to analyze stability, I'm talking about control, it means that the stability main issue, is that to introduce certain type of new artificial, let's say, object, which is tangent plane, and try to say what will happen with the solution if I start here, let's say Z0, return, let's say, follow the continuous dynamics, then jump and return back, not, of course, to the gamma plus, but the tangent plane. And then if I have quite many simulated solutions, and I will be able to recognize this type of three-dimensional object, which is linearization of impact combined with continuous dynamics, which basically represent what will be with respect to deviations from nominal gait. And if this matrix is stable, then, so it's linearization of Poincaré map, then the gait is orbitally exponentially stable. If it's not, then it's not. So again, this surface of codimension 1, so it's in dimension 3. It's okay. Now the question is that what does mean stability in simple words, if you haven't seen it before, is that if I start with red area on that switching surface and move it over the time with continuous dynamics, I hit the switching surface here again by red area and mapped by black, let's say, instantaneous update law, and it becomes inside. And if it's contracting, that becomes stability, roughly. It gets closer, closer, and closer. The question that what I would like to mostly, let's say, talk today is, let's say, people typically consider this as a floor, let's say, floor that hits, hit by a robot as a Poincaré section, or make certain type of constructions about that maps associated with this. Is it a good choice? So it's a very interesting question, because this is physics suggests us. So we are theoreticians, can we suggest something different? And let's, for a moment, forget about that we have a switch. So so this red tube is filled by solutions of continuous dynamics. Of course, I can extend it in negative time and in positive time. Who stopped me doing that? And then the question and of course I can extend not only nominal trajectory, because I know control is 0 here. So it's defined well for any direction, any time. So what I can do also, I think that I don't know exactly the floor. Suppose that the flow is really given with certain uncertainty. So for example, this angle psi, this compass biped works, is eventually perturbed by certain parameter. I don't know is it big or not, but it's basically, if it's different from 0, then this switching surface will be moved and rotated in 4-dimensional space. And it also will be moved and rotated here in 4-dimensional space. So now I come to the point is that, look, so if I forget about the original trajectory cycle, which I'm going to analyze, stability, I can think that I have not one necessary, let's say, nominal switching surface. I have many, because I don't know this age. I never know this age. So we will see that eventually small perturbation of inclination angle, let's say just a few seconds, may destroy a stable walking gait of that compass biped. So this parameter is, of course, it's a scalar here, and it might not necessarily be scalar as well in more practical situations. So, but what does it mean that if I don't know this age? It means that each of these sections valid for me for analysis of stability. I don't know which of them physically realized in practice, in experiment. Okay, now I would like to see another choices for Poincaré sections, and they could be linked already for the piece of the trajectory I extended in negative and positive time. It's not related to the switching at all. So, and what these sections could be is basically something which allows me to say that I can, in continuous time, make transfer or let's say transfers to these sections if I simulate solutions nearby. And of course, I could define it just by vector field on trajectory itself. So it's another alternatives.
Why are you calling that negative time? I mean, it's...
No, because I start somewhere here. You see, it will be immediate. So I start here and continue my cycle.
So this is all in the Lagrangian...
Yes, this is just because negative, this time moments on nominal trajectory doesn't exist. So it's a fake.
Oh, okay.
So, and it doesn't exist also behind this point, it's a fake, but I can simulate it if I don't know really when I reach a floor. Okay, and this type of simple observation that these surfaces are independent on switching becomes very valuable because I don't know where switching happens. And this is what I know very well because this is defined by, of course, it depends how I know Lagrangian itself, masses, let's say distances or whatever, but this could be some alternatives for characterization of dynamics around this cycle. And this is very interesting objects, and I will make number of connections backward in history where they shows up and where these objects becomes very important that people becomes famous for let's say for last 100 years. And so task now would be just to characterize geometrically coordinates or sections itself and also coordinates on that sections. And the interesting point here that let's say it's already not mechanical transformation. So you see, you're given original positions and velocities, standard, let's say, coordinates for description of your dynamics. But I would like to introduce motion-dependent coordinates, which has no this type of clear separation of positions and velocities, so position and momentum. So I would like to say that, look, something which exists on trajectory like S variable, new configurational variable, and then 3 components which designate for me position on that surfaces. So it's equivalent 4 variables, but they have no physical or mechanical clear interpretation. But in these variables, it's very easy to say I am on trajectory or not. So if I'm on trajectory, this is, since it's transverse coordinates, they should be 0 on trajectory. So it's really a scalar representation of that particular curve. And this is what I'm going to say here. Oh, sorry, it's another direction. So it's, let's say, nominal behavior or gait, stable or unstable. So it's not about stability itself, it's just alternative representation of that gait, gives you very compact representation of behavior. So it's 3 zeros and 1 function of time. Okay. So the question only how to find these 3 variables. So it's easy to draw it like that. And the people who found it make number of interesting observations, and we will now comment how it's found, specifically considering examples which are less complicated than compass biped. And what is the less complicated example I know is eventually pendulum on a cart. Let's say system with 2 degrees of freedom, and suppose that I have no force which can move a cart. So a system is passive, the same as a compass biped. There is no impact. So you see that in representation of continuous dynamics, impact is not important at all. So equations of motion, if mass of the cart, mass of the pendulum, distance to from suspension to the center of mass is 1, so meters or kilograms, inertia is absent, then it will be equations like that. System has 2 integrals. Of course, first is energy because system is passive, there is no input. But secondly, it's because there is no force, external force acting along that direction, then you have conservation. And this conservation is eventually conservation of momentum. Let's say center of mass of the system will drive, depends on just how it's originated in beginning. Velocity along that direction. And let's say to see if you've never seen such object, so you could differentiate this momentum and you immediately get the first equation. So time derivative of this twice of x dot will be twice of x double dot, and then derivative with respect to time of cosine theta dot will be eventually cosine theta double dot, and then derivative of cosine by chain rule will be minus sine, and then theta dot squared will show up here. So it's, for students, it's a very good example to illustrate eventually various type of mathematical things. So it's here, it's very easy, don't need to know much. But okay, so the system has 2 integrals, and I write it here explicitly. And then if I look again in these formulas, this relation along trajectory becomes always constant. And I can integrate it once again. You see, it's derivative of x, and this is derivative of sine. So I can write it twice of x plus sine equal to the same value in beginning plus function of time, which is this constant. So it's eventually, this equation is not second order differential equation. You see, it's a strange thing that if I know theta as a function of time, I can compute x explicitly just by initial conditions. And this is what becomes very important relation. So from that dynamical system, we have kinematic relation between degrees of freedom and some effect of, let's say, possible offset of inertial frame. So it means that I will rewrite it in such format. So it's a function phi. So this is virtual constraint we will come to. So it's given by nature for that example, for any trajectory. And of course, the question is that what I would like to illustrate by that example, how to compute transverse coordinates if I'm for the trajectory of that mechanical system if I'm given initial condition. So I'm given certain numbers, position and velocity of x, and angle and angular velocity of theta. So how to find transverse coordinates for that particular trajectory? And there is very easy answer to that question. For two variables, I need to have three components. So its system lives in four-dimensional space. I have a particular curve. It means that I need to have three variables on, let's say, transverse sections. So it will be the first is that just difference between these two minus this one. So it will be function which is zero on trajectory, non-zero outside. Derivative of that will be again function which is zero on trajectory, non-zero outside. So how to find number three? And there is number of choices. And one of them is easy, it's just energy. So I can think about energy minus energy in beginning. But the question is that this is a very tricky thing. So in these cases, of course, it's available, but if I would like to plan trajectories later on, so this energy will not exist. So what I'm interested to illustrate another issue is that I would like to decouple dynamics of x and theta into in these two equations. Because if I know theta, I know x. I have this function. I have this function for computing x if I know theta. So the question only how to find dynamics of this motion generator. I call this theta as a motion generator, generate motion. So what to do is eventually just use second equation and plug x double dot into the second equation, collect terms, and you get just functions depends on theta. X disappears. And it means that I need to solve this second order differential equation for theta. And is it possible from that system to extract one more transverse coordinate? And it's a good point that it's yes. And the point here that you see, you have very specific structure of that equation. It's some function of theta times theta double dot, some function of theta, theta dot squared, minus some function of theta. So this is very famous equation in differential equation, in the world of differential equations. So people in physics know this system very well. This is system which can be, by change of coordinates, converted to the linear one. And if it's linear, you have Cauchy formula to solve it. It means that it's not second order differential equation, it's the first one. There is integral. And this is Bernoulli equation, one of the format of Bernoulli equations. It's not a property that we have obtained it from mechanical system. There exists alpha, beta, gamma, which is not obtained from mechanical system. It's still integrable. So it's basically some type of blossom. So there is integral for any alpha, beta, gamma functions. And it means that I can use this integral and write it energy minus energy in beginning of that particular, which basically separates theta from x completely. So now I have three variables. Transverse components for characterization of dynamics in vicinity of any motion of cut pendulum. Let's come back to the compass biped. So how scalable these arguments? Of course, compass biped has no two integrals. It's not available for me. But if I have a gait, let's say I found by some numerical way or somehow, let's say it gets ingenious in initial conditions to see that it's periodic trajectory, then I can rewrite, because in that trajectory, the stance leg will monotonically move. Monotonicity here is not very important, but it will be in case for that mechanical system. I can use stance leg as a motion generator and try to find this function phi on that gate, which maps this motion generator into the Q2. And it turns out that, let's say, by various reasons, this was called by different people differently. And it becomes one of the most important objects, which basically I learned from Jesse, and afterwards I learned it from other people in mechanics. And it's in control will be called virtual holonomic constraint, and in mechanics will be servo constraint. Okay.
Your name's on the paper that gave it that name, okay?
I just no. No, still, it's not.
I like that name. It's you and Carlos.
Yeah, but it's okay. I mean, I was too young.
Too young.
Yes, because I mean, I show now reference which possibly we need to link to. I mean, it's very bad to invent your terminology. It's okay, and in this particular situation, phi is not sine function like cut pendulum. What we can write is eventually second-order differential equation for phi, which will be corresponding in that relation between 2 degrees of freedom for stable or unstable gait. There is explicit formula for that function f. It's not very complicated function. And also, it's not difficult to see how it comes if you, let's say, try to analyze dynamics, but it's not important at this moment. Okay, so question now that if I plug this function into any of the compass biped equation, I will get alpha, beta, gamma. Automatically generate this expression, which will be integrated because it's again Bernoulli equation, and I will get 3 transverse coordinates analytically. So it's a very strange effect. So just many simple things. I don't need to know mathematics at all here to compute these transverse coordinates for individual trajectories. Okay. And these coordinates becomes very interesting because they are, in some sense, if I try to linearize them, it's not complicated to show that they represent tangent plane, which will be orthogonal to the vector field on trajectory. It means that they are invariant with respect to the change of coordinates. It's also very important. So we're given it we write it in particular coordinates, but let's say they will be always orthogonal to the vector field on trajectory. Okay, and this is what I start to, let's say, making certain type of relations where this example is very important. And of course, there is some conference papers which I didn't print it for you, but again, this is one of the, let's say, break-in result, because it was, I think, I'm not sure if you comment me later on, it was very new at that time. Very new in terms of the proofs, very new in terms of the combination of dynamics, and very new in terms of, let's say, practical importance of this type of result. Okay. I remember it won one of the best paper award in transactions that year. Yep. Okay, and what is about? It's a 3-link pendulum. It's not compass biped. System with 3 degrees of freedom. We have 3 variables, theta 1, theta 2, theta 3. And what was suggested by Jesse is to search, of course, it's combination of control and motion planning, but search for relations. You see, control objectives will be to drive outputs to 0, and outputs now written theta 3 is a function of theta 1. Theta 2 is a function of theta 1, where these functions can be chosen to some extent freely. Or it was polynomial or whatever. So the question now, this is exactly what is transverse coordinates for cut pendulum, for compass biped, but now it's now forced to be 0 or forced to be transverse coordinates on trajectory by feedback. Yeah, is it correct? This is what.
Well, this is short one of your transverse coordinates, right?
Yes, I mean, but there's enough to know that one to compute the rest. So because then derivatives of that, and then you plug it into the passive dynamics and you get collected this Bernoulli equation once again. Okay. So because there is no velocity here, so everything propels the same way. Okay, and now I come to the really material which I learned recently, this one. You see, the question about, of course, it's very difficult to invent something new. It does mean that you don't invent something, but there is, of course, people, I mean, this is a message, not mine. It's told me by my supervisor that all problems you know is solved, or try to solve, it's already solved. It's up to you. You don't know solution. So it's about 1922. So written book, a few, let's say, volumes of mechanics in French, written by Paul Appell, rector of Paris University, where on one particular page, I'm not very good in French, but I try to translate in a very strange way. It was also, I have this book in French and in Russian. I translate from Russian. But I mean, it was very good translation for me. If I really read Russian what is written, I try to mimic what is written now. So the system, let's say, there is a new category of constraint mechanical system, 1922, from considered above. So it's really some type of point 470 is, let's say, volume number 2. For these systems, we cannot ignore method of constraints are imposed. The form of such constraint can be any, even though they often holonomic. The system with such constraint can be seen as a living being, which behaviors are controlled to realize such constraint. So if you define virtual constraint, would it be the same? Okay, again, maybe it's a bit Russian English, but it's, let's say, reflect what was written in Russian version of that translation. Very good. So now I will come to another person. So 1877-78. So George Hill, the problem of restricted three-body problem. So what's the problem? So you have a sun, earth, and moon circling around. So what is restricted is that eventually it's assumed that the moon doesn't affect motion of the sun and earth, which basically follows a solution of two-body problem suggested by Newton. And it was a challenging problem for a few centuries after the Newton, and I mean, many people try to solve it. And they come to the dynamics of, in moving frame of moon, because now we solve problem of motion of Earth around the sun, we know how Earth moves. So we come to the moving frame, and we know that this motion is not periodic. It's really periodic. It's like, let's say, winding on torus physically. But if you come to that particular point of measuring x and y and see what will happen with moon, the dynamics of moon becomes very compact, written as a, say, 2 second-order equations. And it's not anymore mechanic because you see there is no Coriolis terms, there is linear terms because we neglect the effect of, let's say, moon to the sun and earth. But still the system has integral, invariant, which is called Jacobi integral. Everything around that problem has a name. So the question is that, which was a task of George Hill, first to find that there exists periodic trajectory, secondly to prove stability, instability of that. Okay, so what he has done a very important thing. It's eventually a way to transform coordinates from variation. He found periodic trajectory by evaluating infinite series, saying that it's under certain condition it will be convergent. And then around this trajectory, he tried to transfer the coordinates from, let's say, original coordinate system into the transverse and normal. So this is exactly transverse coordinates. And if I see it from perspective of just current knowledge, it's a way to transform these 4 variables into new 4 variables when one of them is rotation around sun, around Earth, one is integral Jacobi, and another 2 is normal deviation from the trajectory, which is periodic, and derivative of that normal deviation. And let's say this variable is not important, it perpetually rotates. Let's say moon goes forward and forward. This variable has negligible, let's say, variation because it's integral, doesn't change, its variation will be 0. And the variation of that becomes a famous Hill equation. So eventually, this guy already developed even more than just Poincaré sections. It's even linearization of dynamics of on Poincaré sections. And what I have also a copy of the paper where it's listed what is written in introduction to the Hill collection of works by Poincaré in 1905. This simple thing is written as the best ever made contribution to science. You see, from now perspective, this is a student work. So, but it's written by Poincaré. Okay, so now another statement which becomes very important. It's so-called Zhukovsky stability. So it's, again, 1882. Let's say this guy published something 10 years before Lyapunov, and he was opponent of Lyapunov's thesis. And he introduced a number of, let's say, concepts which becomes not very popular because in many cases it's simplified to, let's say, less complicated concepts. But we have now examples where eventually this is very important. And what is written here that if I would like to understand stability of particular trajectory of dynamical system, I would like to understand stability. I guess many people introduce stability at that time. You see, it's just a few years after the Hill, 10 years before the Lyapunov. Let's say Poincaré, I think, introduced something similar in about 2-3 years after 82. So, but what is the definition said that if I have number of homeomorphism, which basically transformation of time, which defined on infinite intervals, such that in beginning of the time, it's, let's say, 0, such that for any epsilon, there exists delta based on that epsilon, such that if initial conditions of the dynamical system different by epsilon, then there exists transformation tau, such that difference between, let's say, nominal trajectory and perturbed trajectory will be less than epsilon. So if I put here time, it will be Lyapunov stability. So, but if I put here, for example, situation that I have a trajectory and I have a Poincaré sections nearby that trajectory, moving Poincaré sections. If I, let's say, start trajectory nearby nominal, which basically will intersect all of them. Of course, time of intersection will be different from time from nominal behavior. And this will be this tau. So roughly speaking, it's just analytical way to write what is Poincaré sections. And then, of course, we have also asymptotic Zhukovsky stability if something converges to 0. So this is already written. It was published in, let's say, Proceedings of Moscow State University. Not bad journal at that time. Okay, now we come to some type of concept which I think may be a bit new for that subject over the last 25 years. And I would be interested to see your opinion. So coming back to the compass biped, of course, these guys never considered impacts. They introduced concept, and if I look at the impacts, so I have conceptually two different situations. One is, let's say I can consider, of course, I'm looking for linearization. Everything which exists in nature should be described by a certain type of incremental behavior. And I can consider linearization of impact, even it could be linear, it's okay, it could be nonlinear, but linearization will be designed. And I could introduce certain Poincaré sections associated with continuous arc of my trajectory. And these sections are different. They're not connected to each other. And these sections is good because they are physical flaw. These sections are good because I know coordinates on them analytically, and they're motion dependent. What I would choose to find, let's say, as a Poincaré section for analysis, I will choose this one of them. And this means that I need to somehow redefine impact from physics written here into the sections which are defined here. And how to do it? Is it possible? And this is a picture. Again, it's not much time to explain, but if I look at the just, let's say, gamma plus. So suppose that I have, this is intersection of, let's say, black section, which is a flaw, and blue section, which is associated with Poincaré moving section on continuous arc. So if by impact I come to the black, to tangent surface to the, let's say, real floor, then I need to define somehow initial condition for the system which lives on that sections. To, let's say, it doesn't matter is it in time plus or minus. So I need to initialize this dynamics somehow here. And what could be done, what we can observe is that we know velocity vector field in beginning of trajectory. And in small neighborhood, all vectors will be similar to that vector. So it means that it's just translation. From point A to point B, I need to translate and initialize trajectory on that section and come here. And the same procedure will be with translation defined at this point, where from that section I need to basically rewrite dynamics, find point associated with vector field on the physical flow. So what is outcome of that? So for mechanical system, what we published is certain procedure, analytical procedure of computing for, could be cycle, not necessarily cycle, any motion, forced motion of mechanical system with impact. Certain linear system which now written as variation of transverse coordinates, which will be given analytically with some explicit formulas of A and B matrices, such that you solve this system by period of that cycle or period of this motion you would like to investigate. At the end of the period, you update it by linear update law, because all the translations or linearization of impact is linear, so combination of linear will be linear, so L is computable. And then at the end of the period, I update and solve again this linear system. So this is the simplest hybrid system might exist. This hybrid system depends on the geometrical switching condition. And it turns out that there exists linear system which stability or instability or stabilization equivalent to the orbital stability of that movement, which is very strange. So we change, let's say, switching condition to the simplest one. Let's say, if you have a period 2 seconds, every 2 seconds you need to just solve linear system, update, solve again, and solve again. And let's say exponential stability of orbit here will be equivalent to the, let's say, stability of origin of that linear hybrid system. Okay.
Are you saying this is only true if you do it in the transverse coordinates that you've developed?
No, because it's, if you develop linear system, then you could change coordinates. You could change not just coordinates on the sections, you can rotate the sections, but if it's like equivalence. If you have formula for analytical computation, once you compute any. So it depends only Jacobian of your transformation, you immediately get different type of, you could even compute in excessive coordinates if you like. We've done that as well. Sometimes it's very valuable. So you could, on Poincaré sections, you don't need to introduce number of coordinates listed here. You could have excessive coordinates, which is very important in mechanical system. But in this case, it becomes excessive coordinates for counting number of transverse directions. Let's say we need to have 2n minus 1. We can introduce 3n or 5n because it's easy to compute. Okay, and now come to the stable gait of walking machine. So in this case, it's a stable without input, so input 0, so base is not existing. So what we have done with this computation, we're able to compute, let's say, linearization of transverse dynamics in vicinity of physical orbit. And if we integrate this over the period, so period of this gait, so which is about 7.324, we get analytical representation of Poincaré map as before, but now defined on different section. So it's equivalent. Okay, so now you don't need to simulate anymore. You could basically use analytics to compute linearization of Poincaré map. Even I don't know how to compute Poincaré map itself. I will just compute linearization for that. Okay, so I basically spent all my time, and I think I will just come to concluding remarks and how to use transverse linearization. There is plenty of results which we can immediately obtain from that and just make first conclusions and come to a number of interesting experiments. And the conclusion is that we need to find abilities of robot, like extreme abilities eventually. Robots might have some functionality we're not aware of. It's not necessary to be like human-like, it could be robot-like. And let's say what's the most important part, if you are given controller, suppose that controller is already, there is some type of linear feedback, like LQR, now it's available. You could plan any trajectory. And what's important that if I come back in this system, where is underactuation here? So it could be system with underactuation 2, 3, 4, 5, it doesn't matter. It could be even passive system, I can compute this expression. So linearization-based controller helps to stabilize heavily underactuated systems, trajectories, agile behavioral systems. Okay. And then, so it means that we need to think about representational behaviors and various alternative choices of generalized or excessive coordinates for representation behavior and for representation of these particular relations or transverse coordinates which parameterize behavior. And the beauty of that relation, they can be written as a finite parametric sets. So we have Weierstrass theorem that any trajectory could be well approximated in this space by polynomials or trigonometric polynomials rational functions or whatever. So we get some type of, let's say, approval to approximate very complicated trajectories by finite number of, let's say, parameters not in time, expansion in time, but in certain motion gene rate. And then, of course, there is comparison system for stabilization. So this mechanical system should not be analyzed in this format. We need to convert it into, let's say, transverse coordinates. And then special topics, which I'm very much interested, of course, modeling of underactuated system, because now we use very simplified model of contact. And this underactuation comes into the, let's say, penetration. If you grasping something, you basically use your hand as a passive compliant element. And then, so model-based representation of various type of libraries of behaviors. And then we could think now not experimental-based, but model-based modeling and motion planning or trajectory planning, if I'm correct in this terminology. And of course, model-based motion control for underactuated systems, heavily underactuated systems. And of course, I'm interested in developing benchmarks, common computational facilities or labs, which can, let's say, promote such development. And so at the end, I will show you one of the interesting experiment on underactuated dynamics, which I think maybe, I'm not sure how many of you have seen such person, but you will immediately see what does mean underactuation. So, and you will also see how much, what is the importance motion planning, motion control. So what do you expect the mass of that ball? This guy was moving without grasping.
30 kilograms? 30 kilograms?
Okay, other estimates? So it's a very famous Russian artist. And that was when I was, look at this. So you see, underactuation is something which really could be considered as a challenge because constraints, now look at this. So each of the ball is 40 kilograms. I don't know how it's much in pounds, but it's
about 90 pounds.
90 pounds, okay. No, it's okay. You see, this is underactuated system. Okay. And okay, I think it's enough. I will show you another movie, and I hope we will have time to run this machine. We didn't have time to start it, but let's say this is not a robot. This is what basically you can do. It's just about, let's say, 300 grams. And this is, let's say, examples of what is human capabilities to do many types of interesting motions. It's not just walking. It's eventually, underactuated dynamics is more than just walking. It's something like that. And I would say that this is experiment we have done on, let's say, of course, we are not mimicking by rolling 40 kilograms each, but this is a problem which was formulated by Matthew Mason and Kevin Lynch about 20 years ago. And one of my, let's say, colleagues, Maxim Surov, he was a PhD student at the time, solved it. And over 20 years, it was a challenge. He was nominated at the same time on ICRA on a Best Paper Conference Award and Best Student Paper Award, which I think exceptional. I mean, we didn't get that, but it's eventually, I think, very important. Good, so I think I'm done with the time. Or it's not? No, but because I have much more slides. You know, I have about 60 slides more.